Okay, I've got my trusty calculator here. We are going to look at a work energy problem. This is actually from 9-C2, problem number 22. And what we have here for work energy is we have a 1,300 kilogram car coasting along a horizontal road, nice and flat, with a speed of 18 meters per second. After it crosses an unpaved, sandy stretch of road 30 meters long, its speed decreases to 15 meters per second. What we'd like to find is what is the network done on the car. Well, was that network positive, negative, or zero? And to kind of describe why. And then what is the magnitude of the average net force on the car in the sandy section? Well, let's start this off like everything else in life with a little picture. It doesn't have to be beautiful or anything, but essentially what we have is a poorly drawn car by yours truly. Honk, honk. Person in there, I guess, or maybe the car has eyeballs, who knows. Here is our little section of whoosh, whoosh, sandy road, and then here's our car, once again poorly drawn, on the other side. Okay, we know initially this car has a velocity of 18 meters per second. At the end it has a velocity of 15 meters per second. So we know this car is going to slow down. We also know that our sandy road here has some distance of our displacement of 30 meters. Okay, and I guess we'll just tack it up for good measure. The mass of our car is 1,300 kilograms. So for part A, what we're looking at, we're just trying to determine, is this net work done on the car positive, negative, or zero? And to explain that, well, we know that the work done on this car is going to be negative. The reason being is our car has slowed down, which means there is some force opposing its motion. And if we kind of think of this sandy gravel here, there's some friction going on there. And if we were to draw these forces out, we would actually see that this gravel slowing us down, it's got a frictional force pushing against us, while we in the car are moving to the right with some velocity, some delta x. But we are slowing down. If we wanted to mathematically kind of justify this, well, if there was some force and we looked at the work itself, remember work is W equals F dot delta x. And this dot product's really important because it's not just multiply, you're taking an angle into account as well. It's F delta x cosine of some angle. And if we look at our force and displacement, we're looking for the angle between those, and that angle is going to be 180 degrees. And we know that from the unit circle that the cosine of 180 degrees is equal to -1. So the work we're going to find here is going to be negative from that cosine F delta x. So right there, we can pull our negative out mathematically, or we can justify this in saying that, hey look, the car is slowing down. Some force has to oppose its motion. Anytime a force is opposing the motion of an object, that work is negative. So we know the work's going to be negative there. For part B, to find the magnitude of the average net force on the car in the sandy section, well, since we have a velocity, initial, final, a mass, and a distance, what we can actually use is we can use our work energy theorem. If we remember from the derivation of it, we know that F dot delta x is equal to 1/2 m Vf squared minus Vi squared, where everything on the right here, the 1/2 mv squares, those are kinetic energies, and on the left we have F dot delta x, which are the works. So if we take a look at this, we already know what our work's going to be. We're going to have a negative, the force, which is what we're looking for, and this is technically an average force over this distance. We know the distance of the sandy path is 30 meters. This has to equal 1/2, that's always a constant. We know the mass of the car, 1,300 kilograms, and we know some velocities here. we know the final velocity is 15. Don't forget your square. That's in meters per second. Minus the initial velocity, 18 meters per second. And don't forget to square them. Okay? Everybody always forgets to square these and to square them before you do the subtraction. So if I wanted to kind of go ahead and solve this, what I would do first is I'd get this 15 square and 18 square out of the way. So 15 squared, that is 225 meters squared per second squared, kind of a weird unit. 18 squared is 324 meters squared per second squared. And if I subtract that, 225 minus 324, I get a quantity of negative 99 meters squared per second squared. Okay? So that was just me working down through that square. That's going to be where you make your mistake if you're going to make one on this, because the rest of it's fairly straightforward. Writing the rest of the problem back in, we've got our 1,300 kilograms again. We've got our 1/2. We've got our 30 meters. And we've got our negative force. Okay. At this point, we can just kind of start solving everything out here and solve this completely. Looking at this, even though this is a meter squared per second squared over here, I kind of have a good intuition that things are going to pan out how we want them. A kilogram meter per second squared is a Newton. That's MA. And when I divide each side eventually by this M, I'm going to cancel one of these M out. So I know I'm going to get newtons here. I feel pretty good about that. Let's just get this math going. I'm going to do 1/2 of 1,300. So 1,300 divided by 2, that's going to be 650 kilograms times negative 99 equals 30 times negative F. 650 times negative 99 gives me a giant number. It's going to be negative 64,350, and technically my units here are kilogram meter squared per second squared. On the other side, I've got negative F times 30 meters. When I divide by the 30 meters on each side, one of my meters divides out. So look, like I said previously, we've got our kilogram meters per second squared. That's a Newton. That's a force. We feel good about that. So we just have to say, hey, negative 64,350 divided by 30 equals, so our negative force is going to be equal to negative 2,145 newtons. And because we have a negative on each side, the negatives wipe out. So there's our answer right there. The average net force is a little over 2,000 newtons acting on the car. So that's just kind of going through that. Really, it's all just a matter of setting up the equation. We know which equation we're going to use here. It's going to be our work energy equation. And then from there, it's just a matter of carefully doing the mathematics so that we don't mess anything up. Okay? So that's what we're kind of looking at for a work energy problem. It's nothing too crazy. Just be careful with those squares and subtracting those values out. But with that, that problem's finished.